So this is the last class of the course, and our last topic is constant false alarm rate detection. Now if you work on the detection, either in industrial or in academia, you will hear this term, constant false alarm rate, and there are multiple definitions for it. I'm going to introduce two. Of course, these definitions are all linked. Okay, so we have a problem, and this problem is parameterized by the parameter theta, and the parameter theta may have some unknowns. Okay, so the value of the parameter theta is not entirely known. Okay, this may be the case under both null or alternative hypotheses. So under the null hypothesis, we want to keep the false alarm rate constant and then maximize the probability of detection. So we are essentially looking for a test phi so that the false alarm rate is constant. That is, the expectation of phi under the null hypothesis is all constant alpha. And then we maximize the expectation of phi, assuming that theta belongs to the set cap theta sub 1. All right, so that's one definition. Another definition of the CFAR is that we have a test statistic, and the distribution of the test statistic does not depend on the unknown parameter under the null hypothesis, in which case, of course, we can set the threshold irrespective of the unknown, and we can set the threshold constant as we wish. Okay, so anytime you have a test statistic, and this test statistic does not depend, the distribution of the test statistic does not depend on the unknown under the null hypothesis, that test is called the constant false alarm rate test or detection. Okay, so of course these two are related. Obviously, if our test statistic does not depend on the unknown, we can then set a threshold not only to make this maximum, but also perhaps attempt to maximize with respect to the probability of detection. All right. So there are, depending on the problem that we have in hand, this might be addressed in a different way. But one methodology in addressing this is based on the so-called invariance principle. So let's assume we have our parameter set theta, and it has two components, phi, which is the known component, and epsilon, which is the unknown component. For example, we may like to detect a signal embedded in noise, but we don't know the noise statistics. In that case, the variance of the noise could be the unknown part of the parameter theta. And of course, the knowledge of phi is needed, but nevertheless, this is a nuisance parameter because our main objective is to determine which parameter value is to choose. Okay. All right. So we have our observations x, and that of course parameterized by this vector theta. Okay. All right. So for example, we might have this particular test where, let's say, phi is a amplitude of our signal. Phi being 0 means there is no signal. Phi being larger than 0 means there is signal. Okay, so this can be signal present, signal absent problem, and phi sub 0 could be, let's say, noise variance. Okay, so here epsilon, of course, is not known, and for a test of this kind, uniformly most powerful test may not exist. Okay, it usually does not exist. Now, we can invoke invariance principle, and of course it does not mean that we will be able to use this principle always, but nevertheless we are looking for a function z from our sample space X to another space Z, such that this mapping Z contains as much information about phi, which we want to determine, as the X itself, and that the distribution of Z does not depend on the function on the unknown parameter epsilon. Okay. In that case, of course, we are going to map everything to Z, and then redefine our hypothesis testing. And in that case, we can simply eliminate the unknown phi and define a one-sided test, which is a simpler test than the one-sided test with unknowns. And most likely we would be able to find a UMP test on this, for example, based on monotonically increasing likelihood ratios. Okay, so let's look at an example, a classic example where CFAR tests are desired is the signal present, signal absent problem. So we are observing X sub I, and X sub I may be simply noise, or it may be the signal plus noise. This is a classic problem that you would encounter in wireless communication, where you are sending a signal S sub I as a bit, a symbol of the bit, and as it travels through the channel, it gets corrupted by additive noise, W sub 0. Or you may be simply observing the ambient signal, that there is no signal, okay? Or it could be radar sonar problem where we transmit a signal, and if there is a scatterer out there, it's going to reflect back to the transceiver, and we will observe signal plus noise. Or the signal will indefinitely propagate, and we will simply observe the noise, okay? So here we are, we vectorize the signal S into a vector of dimension n, and of course signal is known, and we vectorize noise into a vector of dimension n. We assume that the noise is zero mean, and its covariance is R times sigma square. We know R, but we don't know sigma square. In other words, we know the autocorrelation function up to a constant, and that sigma square is essentially represents the energy of the noise, okay, or noise power. All right, so we can first, for example, consider the likelihood ratio test. Okay, so we can assume the likelihood ratio test. We've solved this problem before. This is a pre-Whiten matched filtering problem, or matched filter. So we have S transpose R inverse X. Here R inverse, of course, X is a pre-Whitening transformation on X, and then pre-Whiten measurements are matched to S. Okay, so this is the test function for the log likelihood ratio test, and we compare that with a threshold gamma. Now, so if you look at the test function S transpose R inverse X, this may not depend on sigma square explicitly, but its distribution under both null hypotheses and alternative hypotheses depend on sigma square, because X is Gauss with zero mean and covariance sigma square R under the alternative hypotheses, and it's Gauss with mean S and covariance sigma square R under the alternative hypothesis. So in both cases, the distribution of the test statistic depend on the unknown, therefore log likelihood ratio test is not a CFAR test. Okay. Now next we may consider generalized likelihood ratio test, see if we can obtain a CFAR test using the generalized likelihood ratio test principle. So to form our test statistics, we form simply the likelihood ratios, but since the conditional distributions depends on sigma in both cases, we simply estimate sigma by means of the maximum likelihood principle and plug our estimate back into the distributions, conditional distributions. So here is the conditional distribution of our measurements under the alternative hypotheses. So it's Gauss with mean S and covariance sigma squared times R. And here is the distribution of our measurements under the null hypotheses. Again, it's Gauss with zero mean and covariance sigma squared times R. Okay. All right. So since sigma squared is not known, we have to estimate that. We of course invoke the maximum likelihood principle here. And if you do the maximum likelihood estimate of the unknown sigma under each of the hypotheses, we see that that's simply a sample mean. Okay. So we plug these values in to the ratio and simplify, and after doing the necessary arithmetic, we see that the GLRT statistic reduces to the ratio of the two quadratics. Okay. Now, does this depend on the unknown sigma square under the null hypothesis? That's the question. So to see that, let's write X as sigma times W tilde, where W tilde is a process with zero mean and covariance R. Okay. Now take this and plug it into our generalized likelihood ratio test statistic, and we see that we cannot really cancel out sigma square from this ratio, and hence the ratio, actually the test statistic, generalized likelihood ratio test statistic, depend on the unknown under the null hypothesis. Therefore, GLRT is not a CFAR test. Okay. All right. Okay. So now let's consider another problem to see if we can obtain a CFAR test. This is the case where, again, we don't know the noise variance and we don't know the signal amplitude. We can formulate the problem as observation being equal to noise under the null hypothesis, or observation being equal to A times S plus noise, where A is the unknown amplitude, S is the known signal, and of course W is noise as before with zero mean and covariance sigma square R, sigma square unknown and R known. All right, or we can alternatively formulate this problem as A being equal to 0 under the null hypothesis and sigma square being sigma sub 0 square, or under the alternative hypothesis A is different than 0 and sigma square is equal to sigma sub 0 square. So in that case, of course, the theta is going to be composed of A and sigma square, where A is the main parameter of interest, sigma square is the nuisance parameter that is not known. Okay. So since both A and sigma square is not known, and we would like to check whether GLRT is going to produce a CFAR test for us. We need to estimate both A and sigma square under H1, because under H0, A is 0. Okay? So here is the conditional distribution of X. Again, Gauss. And we maximize the conditional distribution of X under the alternative hypotheses with respect to A and sigma square. Taking the logarithm and setting it equal to 0, we can find out the maximum likelihood estimate of the signal amplitude being equal to the ratio of these two quadratics. So now looking at here, we see that this looks independent. I mean, this is independent of sigma square. We don't see sigma square, but obviously the test statistic under H sub 0 depends on sigma square. Now next we estimate the variance of noise under the alternative hypotheses and the null hypotheses. So we plug in the estimate for A and take the log and set it equal to 0, and that gives us this sample variance estimate, and we have the estimate of A inserted here. Under the null hypothesis, we had the same estimate as before. Okay, so now we have the ML estimate of A and the ML estimate of the noise variance under the null and alternative hypotheses. We are going to plug these estimates into the generalized likelihood ratio test statistic. So if we do that, we plug this in, and now we would like to understand whether this ratio depends on the unknown sigma under the alternative hypotheses. We apply the same trick. We write X as sigma tilde times W tilde times sigma, where W tilde is Gauss with 0 mean and covariance R, and plug this model into the GLRT ratio. Now we see that we can actually, in this case, eliminate sigma from the ratio. It cancels out, and what is left in the ratio, nothing depends on the unknown sigma, and now we have a test statistic whose distribution does not depend on the unknown under the alternative hypotheses, and hence we can set the threshold to a constant rate of our choice, irrespective of the knowledge of the unknowns. So therefore, in this case, the GLRT gives us a CFAR test. And with this, we end our class. I hope you all enjoyed the topics, and it was a pleasure to have you all in class. We had to do some major changes and adapt to a new mode of lecturing and communicating in the second half of the class. I wish you are all safe and sound, and hopefully we will get through this in the next couple of months. Bye-bye.